Hello, everyone. It's time for physics. Today we're going to talk about sound, and specifically, what makes noise.
Sound the way that it does.
Now, these real-time graphs help us visualize how sound looks. I'm going to play some stuff here on the keyboard, and I want you to observe the graphs and see if you can figure out what these graphs are telling us. My synthesizer is generating tones from an electric signal. This electric signal is sent to a speaker, like the one in your computer or earphones. The speaker vibrates based on what the electrical signal is telling it to do. You can imagine this graph as what the speaker is physically doing to make noise, or how your eardrum is vibrating to receive the sound. The bottom graph is a plot of the frequencies that are present in the sound. To understand these graphs better, let's consider a pure tone, a single frequency. Tuning forks are good at producing pure tones. So is a whistle. To get more consistent results, I'm going to have my synthesizer mimic a whistle for me. Notice the shape here. It's a beautiful sine wave. This means that the speaker is fluctuating the air in a nice, smooth, back and forth way. Also notice the frequency plot. There is one peak indicating that I am whistling at almost a single frequency. If I play 3 notes on my keyboard, you can see the 3 corresponding peaks of frequencies that make up the sound. What we are doing here has a name. It's called spectrum analysis, and we will use it to look at the 3 characteristics of sound: pitch, loudness, and timbre. Perhaps the easiest thing that a human can differentiate between 2 sounds is the pitch, or how high or low the tone is. Physically, the pitch of a sound is the frequency of the sound wave. Here's an A note playing at 440 hertz. Notice how far apart the wave peaks are. Here's an A note 1 octave up at 880 hertz. Notice how the wave is pushed together. This is what a higher frequency looks like. This means that the speaker is going back and forth faster with a higher frequency. And the faster back and forth of the air is what our brain recognizes as a higher pitch. I'll play the C major scale here so you can see how the frequency of each note changes. The second quality of sound that is relatively easy for a human to perceive is how loud or how soft a sound is. In terms of a speaker jiggling, the loudness corresponds to the amplitude of the wave, or how far the speaker will extend from its resting position. Notice how the amplitude of the wave increased when the sound got louder. The displacement of your eardrum is what your brain perceives as how loud the sound is. Loudness also depends on how far away you are from the object making sounds. The further you are away from a sound source, the quieter you will perceive it. Timbre is probably the biggest reason why 2 sounds could be different from each other. For example, an E note on a guitar sounds different than an E note on a keyboard. Timbre comprises three main characteristics: harmonic content, sound envelope, modulation, and other effects. If you play a single note on a guitar, you might assume that you are only playing a single frequency. In reality, when you pluck a guitar string, there are a number of overtones that vibrate on the string. Sure, the main peak is the loudest one, but the reason why a guitar sounds the way it does is because it will constantly sound these intervals of overtones due to the way the strings vibrate. This also holds true for wind instruments. Flutes have a different arrangement of harmonics than clarinets, and both of those are different still than a singer. To show you slowly how different harmonics impact the sound, I will slowly bring in different harmonics on this sine wave that we have been working with. Yet another way to get a different sound is to change the way that we are driving the speaker. Not all sounds are nice, smooth sine waves. There are square waves, there are triangle waves, and there are sawtooth waves. By changing the shape of the sound wave itself, all we have done is added more harmonics to the sound. The easiest way to think about sound envelopes is how the volume changes during the lifetime of a sound. A guitar sounds its maximum volume as soon as it is plucked, and the volume slowly decays away. You can program a synth to fade into its max volume and out again slower. This is called the attack and decay of a sound. Here's an example of a sound with a sharp attack and a sharp decay. Here's an example of a sound with a longer attack and a longer decay. We're used to sounds that attack sharp and fade away slowly. If we program the opposite to happen, a slow attack and a sharp decay, we can get a reverse-like effect. There are two fundamental types of modulation. You can modulate the volume of the sound. This is called tremolo. I'll demonstrate this on my guitar. Or you can modulate the pitch of a sound. This is called vibrato. You can also replay a sound repeatedly after an initial sound is sounded. This is called delay. Certain types of delays will add tremolo or vibrato to the echo for an added effect. Let's step back and look at the big picture here. Every single sound that you hear is made up of these elements. Your favorite songs are pleasing to you because of a combination of all of these characteristics and more. When you were younger and you were learning the sound a cow makes, what actually happened is that you were training your ears to pick up on the subtle variations of all of these characteristics of sound. And finally, imagine your best friend. Can you hear what their voice sounds like in your head? Their voice has a unique tone, a unique loudness, harmonic content, attack, and decay that make up their own voice. These characteristics of sound aren't just oscillating graphs. They are how animals have communicated since they could disturb the air around them and pick up those disturbances from others. That is sound.